So in this class on coordination complex compounds, we shall look into how chelate formation actually enhances the stability of a coordination compound. So just to take a quick review what chelation is, it is basically the closed loop structure formation when a di or multidentate ligand forms multiple coordination bonds with the same central metal atom in the complex compound. So just to give you an example, the ethylene diamine, which is a popular example. So this ethylene diamine ligand, here you can see it has two nitrogen sites. The ethylene diamine ligand, it has two nitrogen sites on each side of the ethylene group. And both of them, when they form the coordination bond with the metal, same metal, then they end up forming like a closed loop structure. And the equivalent of this can be written down when two ammonia, which are unidentate or monodentate ligand, they form two separate coordination bond with the metal. So we shall look into the further discussion that how this closed loop formation or the structure formation, it actually gives much more stability to the complex compound than just having the two similar type of bond formation from the unidentate ligand. So to explain this or to understand this, we have taken the example of these two reactions, and we here, let's say we are systematically replacing the 6 water molecules of this nickel aqua complex in one of the reaction by 6 ammonia. Now we know that ammonia is a strong field ligand and water is a weak field ligand, and one can actually replace these or displace 6 water molecules from this complex compound by 6 ammonia. So one molecule of this nickel aqua ammonia complex exchanges its 6 water molecule with 6 ammonia molecules to form one molecule of nickel hexaamine complex, and 6 water molecules are displaced. And if we measure the stability of this particular formation of nickel hexaamine complex, it turns out that the stability constant or the equilibrium constant for this particular process is enormously high at room temperature. So it is about 4 into 10 to power of 8. So that simply suggests, the value itself simply suggests that this process is enormously favored in the forward direction. That means the stability of this form of nickel complex with ammonia is much more higher than this complex of nickel with water. And here we have not yet talked about anything in terms of the chelate formation or the closed loop formation. This complex compound will still be like you have 6 separate ammonia molecules forming 6 coordination bond with the central metal atom. All right. Now let's take the another reaction in which I'm taking the same particle or same molecule of nickel hexa aqua complex, and now I'm displacing the 6 water molecules with just 3 ethylene diamine molecules or ligands. So this ethylene diamine is abbreviated as EN. Okay, this is known to us already. So ethylene diamine, 3 ethylene diamine will be required to replace 6 water molecules. And ethylene diamine is also a strong field ligand, and it can displace, and it will lead to the formation of nickel tris ethylene diamine complex compound, complex entity. And here also you get 6 water molecule displaced. So the difference here and here is only this, that here you have 6 separate monodentate ligands involved in the formation of 6 coordination bond with the metal, and each bond exists separately from the other. But in this complex formation, each of ethylene diamine is involved in the formation of 2 coordination bond with the central metal, of course in octahedral geometry overall. But then there are 3 closed loop structure formation like this will happen in the formation of this complex compound, while there is no closed loop formation of structure in this particular complex compound. What I mean by is this, if I try to draw the structure here, I can show you, let's say nickel, and there are ammonia, NH3, NH3. If we consider these four ligands in one particular plane, then above and below this plane also there are two ammonia. So this way we have the formation of octahedral geometry. Okay, just to give a certain perspective, I can simply make a boundary here, something like this. And if I try to show you the structure formation of this, then it has to be nickel. And but now I have to consider the each En forming one closed loop. So let's say if I take one ethylene diamine forming a closed loop like this, okay, I am representing this ethylene diamine in an abbreviated form, but it is understood that what I am trying to represent by this formation is something like this. Okay, all right. And other ethylene diamine, now you have to consider the formation of other ethylene diamine. One can consider the other ethylene diamine forming a closed loop here also, and the another ethylene diamine can form a closed loop above and below this one, nickel. But let's just consider a particular complex formation in which I am considering the formation. So let me just put a little bit. Let me represent this one plane of octahedron. Let's say central plane of octahedron. And here I connect, let's say, this bond and one bond here through ethylene diamine. And then I connect this bond and this bond below the plane through another ethylene diamine. So this is one type of nickel ethylene diamine complex formation, okay, where you have three loops that you can see, closed loop, they are formed while the formation of this coordination compound is happening. And in doing so, see, our starting material is same in both the cases. Our ligands are different. One is a monodentate ligand, in another case we have a didentate ligand. And when these complex formations are happening, actually one can see that the nature of bond that is being formed is more or less similar. Here also the bonding is actually happening between nickel and ammonia or nitrogen of ethylene diamine, which is like an H2 amine group. So this nature of bonding is more or less same. I would say that there will be hardly much of difference in terms of enthalpy if we just consider the bond enthalpy of nickel and amine group. So the bond enthalpy wise it could be very similar in both the cases. All right, but then when we measure the stability constant, or let's say the equilibrium constant for this complex compound, it is much higher than what we saw in the previous case. You see, already we said that this displacement reaction leads to the complex formation which is enormously stable compared to this complex compound. But then when we try to create a complex compound by using a didentate ligand, maintaining that the nature of bond still remains more or less similar, the level of stability that is reflected to the measurement of equilibrium constant is much enormous. So it is 2 into 10 to power of 18, that is also measured, let's say, at room temperature, and compared to this it is much more higher than this one. So then we should actually explore the reason behind this. Is it because of the very enormously different thermodynamic parameter? Let's look at that. And in order to gain deeper understanding of this, we will definitely have to compare the values of the free energy, the standard free energy. One can actually get this standard free energy values from this equilibrium constant. We already have known this relationship that delta G0 is equal to minus RT into ln, which is log of E base K. K is the equilibrium constant here. So R is a gas constant and it will have a value considering the unit of energy, that is 8.314 joules per mole into Kelvin, K for Kelvin, and T is the temperature here in Kelvin. So we can see here, if we substitute these values, and in our case the temperature will be here 298, because I said that these values of K are calculated, let's say figured out at room temperature. So for us, delta G value or delta G0, which is the standard free energy change, can be obtained by taking 8.314 into 298, which is in the Kelvin unit. I take room temperature as 25 degree Celsius, and then if I take here the value of log of K 1, then I get delta G1, and if I substitute this number here, this K1, then I get this value of delta G1. Similarly, I can substitute the value of K2 here and I get delta G2. So now let's compare directly the values of delta G1 and delta G2. So we already know that in a spontaneous process, the delta G negative value, higher the value of, much more negative the value of delta G, that also reflects the stability, enhanced stability of the product. So delta G here is much more negative compared to the delta G value here. And this suggests that the stability of this is enhanced much more than this. But then in order to investigate the reason for that, we should look into the thermodynamic factorization of delta G into the enthalpy parameter and the entropy parameter of the reactions. So basically we know this particular relation where I am relating the standard free energy in terms of the energy changes that are happening in these processes, which are reflected in terms of enthalpy, and the energy changes which are equivalent to the entropy changes, or the changes in the randomness that are associated with these processes. Now to go further, the temperature is maintained constant in both the cases. So if there is any change in the values of delta G, it has to occur if there is any change which is there enormously. We can see here this is much more negative than this one, which shows that this is much more stable than this. So any change in these two values, they must be either occurring from delta H or from delta S. Now I have already told you the way in which we have designed these reactions. We have tried to maintain the nature of coordinate bond that is being formed between the ligand and the metal is more or less similar. You can see here also there is a nitrogen involved forming the coordinate bond with the metal, and that nitrogen is also coming from ammonia, and here also the nature of bond that is being formed between the metal and the ligand is close to similarity, because here also the bond is being formed between the amine group of ethylene diamine and the metal. So bond strength wise or the bond enthalpy wise, this difference is very minimal between this complex formation and this complex formation. And here we are starting with the same complexes in both the reactions. So naturally the enthalpy changes which are associated in these two reactions, let me write it down here. Suppose delta H10 is the enthalpy change associated with this process, and delta H20 is the enthalpy change associated with this particular process here. So in these two cases, for us what we may find is delta H10 is very close to delta H20. That means there will be hardly any difference that will be caused because of the contribution of enthalpy change of the two reactions in the value of delta G1. Alright, so what I mean is, if I consider this equation for the first process, then I write here delta G1 is equal to delta H10 minus T into delta S10. And for another reaction, if I write here delta G to 0, that is equal to delta H to 0 minus T into delta S to 0. So all I'm saying is if delta H1 and delta H2 are very similar, then this difference, further difference between delta G1 and delta G2 will have, okay, the only contributing factor, it doesn't really matter if I'm just comparing the value here. I can otherwise write here delta G2 minus delta G1. The difference between the free energy values, which is this minus this value, will be primarily, so if I consider this approximation here valid for this above set of reactions, then I simply say that the difference is primarily entropic. That means I should say that delta S10. So this delta G value difference between these two reactions primarily is attributed to the entropy change associated in the processes. And how is that? Let's understand that, because as I said, this will, with this approximation, the two factors cancel each other. So this difference of delta G can be understood in terms of entropy change. For example, if I say that delta S10 is the entropy change associated with this process and delta S20 is the entropy change associated with this process. Okay, so can we understand that the delta S2 is much more different than delta S1? Yes, let's look at this one. See, we will not go into the detail what entropy and how this parameterization and all those things right now. In a very simple term, at this point of time, we can just consider the kind of randomness that will be caused because of the change in the number of particles that are involved in the process. What I mean here is, let's say there is one molecule of this complex compound reacts with 6 molecules of this and finally leads us with 1 molecule of the complex compound and 6 molecules of water. So if we see here, the total number of particles that are on the left hand side of the reaction and the right hand side of the reaction, they are more or less similar. They are same basically. And therefore, whatever randomness, statistical randomness that will be associated with the number of particles, the randomness which simply, let's say, is considered to be dependent on number of particles, that will be more or less similar on both the sides. So I'm not saying there will be no difference of entropy on both the sides, but let's say whatever is the difference of entropy here in this particular process will be of a very minimal magnitude. But then compared to this, if I look at this reaction here I see that 1 molecule of this complex compound reacts with 3 molecules of ethylene diamine. And on the other side, what we get? We get 1 molecule of this complex compound plus 6 molecules of water. That means I'm saying here that if I represent the entropy on this side as S initial, okay, S0 initial, and if I represent the entropy on this side as S final, okay, S0 final, then S20, that is the difference of S final 0 minus S initial 0, is actually quite positive, because you see that this is like 7 and minus 4. So this is a positive number. This whole thing is a positive number. It's a positive value. Okay, we are not counting just that this number difference is the entropy difference, because there is a relation. But then all I'm saying is, more the number of particles that are created, higher is the randomness that is happening now compared to what was the situation previously. You can think of, suppose if there is a class of just 5 children versus in the same class if you have 40 children, the kind of randomness or the kind of possibility that how the children will occupy various locations in the class, that will enhance enormously when there are larger number of children. So the randomness of the system statistically is enhanced, okay, and that will contribute to the entropy parameter. So all I'm saying in this particular reaction, that since the number of particles that are on the product side are much more than the number of particles that are on the reactant sides, the entropy enhancement will happen. That means the delta S to 0 is a positive value compared to the delta S1 in this particular case. Now I do not know exact number here, so I can't say that whether it is how much this value will be. But I'm saying, suppose if I just associate these differences with the entropy changes, then let me also say that in this particular case, suppose if I say the entropy associated here is also Si initial, and this is SF0, F for final, I for initial, then SF0 minus Si0, I can say that it will be either a very small number, or let's say, okay, maybe I should say very small value, because the difference is quite very small, okay, but in this case the difference is enormous. This difference will lead to enormous change in the entropy, and that's why it's a very high positive value. I should say here high positive value. And now if we come back to this equation here, so we see that delta S2 is much bigger than delta S1, 0, and therefore this number is positive number. So this entire number is a positive value. If this difference is a positive value, then the difference of free energies of these two processes, okay, whatever differences, that will be, if I write here delta G2 0 minus delta G1, then it will be a negative value, because there is a negative sign here. Positive negative will become still a negative, so I can write here less than 0. Now what I mean by writing this, I'm trying to say that delta G2 0 is much more smaller, or it is much more negative than delta G1 0. So this is much more negative, this is more negative than this one. And that simply suggests, actually, because we have already established, or we have understood, that more negative the value of delta G for a particular process, higher is the stability of the product formation, or higher is the stability of the products that are formed in that particular process. So much more negative value of this free energy change in this complex formation, where you have the chelate formation, it leads to enormous enhancement in the stability, primarily due to the entropic reasons.